Okay, there we go.
Okay. Hello, everyone. Welcome to the Lab 5 help session. This is hosted by me, Daphne, and Davis. And let's go through some of the useful topics for this lab. So we're going to explain ASM's algorithmic state machines. We're going to give some examples on making an ASM and interpreting an ASM to create a next state truth table. And then we're going to go over using VHDL, an example of VHDL, and also give a little bonus section on some advanced VHDL that might be very useful to you. So let's see. So the first topic, what is an ASM? It's an algorithmic state machine. An ASM is a way to, sorry, there's echo. Um, A finite state machine is basically the concept of what you've already been making with counters. So it's when you have a system where,
Yeah, I can turn the yeah.
sorry, I was dealing with echo from the recording. So it's a system where you have a collection of states. These states are represented by certain state bits. And you also have transitions between these states based on the current state and based on any possible inputs to the state. Based on the state, that may represent some outputs. So you may represent this finite state machine with like a simple flowchart, like you've been making with counters, like numbers that point to each other. You can represent them with a next state truth table where you have the current state, the inputs, and that corresponds to an output of the next like state bits and the outputs. Or you can use an ASM, which is a more structured way to represent a state machine. So we're going to go over the characteristics of an ASM because it's the actual like flowchart that you're going to need to draw for this lab. And I guess some guidelines for translating certain like properties of the state machine into an ASM design. So an important factor of ASMs is you have two types of outputs. You have Mealy outputs and Moore outputs. Moore outputs, well, I guess I'll start with Mealy outputs. Mealy outputs can be like, Mealy outputs are outputs that can change during any point of like the state machine's existence, whereas Moore outputs can only change on clock cycles. So the mnemonic you use to remember that is immediately versus wait some more. So Moore outputs will not change until the next clock cycle is hit, whereas like Mealy machines, if you have like some sort of input that's changing during a clock cycle, at the point that the input changes, and like you might have a conditional like if if this button is pressed, then at any point that that button is pressed, if you have a mealy output, it's going to be triggered as soon as the button is pressed. But if you have a more output, the button needs to be pressed like during a clock cycle for the output to actually change. And the output is going to stay changed until the next clock cycle. Whereas for a mealy output, it will change back as soon as you depress or unpress that button. So the purpose of an ASM is that as you get to more complicated designs, like more complicated state machines, it's just a lot easier to represent the behavior if you use like this kind of pre-made structure. And you're going to see this in the future, in Lab 6 especially, and once like later on in Lab 7, you're going to be interpreting a pre-made like computer system called the GCPU. I think you guys went over that today. So there's going to be a bunch of like state machines inside the document that represents like the entire design of the Gator CPU. So you're going to need to be able to interpret like what is the state machine doing. It'll be like for commands that are using the CPU. So like what is this state machine doing and how do I expand upon it? So with that over the way, with that out of the way, the symbols that we use to represent different types of outputs. We have a rectangular box that represents a more output. So every time that an arrow goes to a rectangular box, like that transition will happen at a clock edge. Whereas if you have an arrow going to a mealy output, that'll be represented by a circular shape. And like as you're flowing through, like as you're tracing through an ASM by yourself, once you hit like once you hit one of these circles with an arrow, it might be from a conditional or it could be like directly from a more output. Like you could have an arrow going from one of these more outputs to a mealy output without anything in between. So as soon as you hit that circle when you're like tracing through it, that output will be triggered or the output will be set to true. And another note, whatever output, like the name of the signal that is inside the box, is always going to be true when it's inside one of these shapes. So, like I kind of mentioned, anything mm, anything between two boxes represents a state, and anything inside of a box is always true for the entire state. And so you can see at the upper left-hand corner of these rectangles, that would be the name of the state. Everything that happens, like, I guess my cursor isn't really following it. Okay, so let's look at this state. So this box with A inside of it, this is a more output. This is saying at the clock cycle, when it goes to this, the statement will be 0, A will be true, and then we look for the conditional. So is the switch on? If it's true, then we do the output of C and then it goes to whatever like next state after a clock cycle. Otherwise, if the switch is not on, after a clock cycle, you can see because of this rectangle, we then transition to state B. So that's kind of how you trace through it by yourself. Okay. So now we're kind of moving on to interpreting ASMs. So we have a system. We want to represent the system with an ASM, except we know that A and C cannot be on at the same time. So we want to check, is this ASM a correct representation of this state machine? So we start at the beginning. I always look at literally whatever state bit 0 is. And we know that during this state A, for this entire clock cycle, because A is inside of this rectangular box, A is going to be true. From there, it's kind of the same ASM as the last slide, where during this state, we check, is the switch on? And if it's on, then we turn C on. If it's off, then we will progress to the next state at state B. So in this case, we know that A is on when the state starts, and if the switch is on, then C is also going to be true. So that means both A and C may be true if the switch is on during this clock cycle. So this ASM is not correct because it displays a behavior where A and C can be on at the same time. So let's see. This ASM is not correct. Do not do this if you have these conditions together. So now what we're showing is an example of a correct ASM that displays the behavior we're probably trying to show. So you're going to have a state with, you can have like one of these rectangular boxes with nothing inside of, because this just represents a state where all of the outputs happen to be false. And so if we're at state A, then we check the conditional. If the switch is on, then C will immediately be output. And if the switch is not on, you can see you have a 0 next to the subscript that just represents like the truth value of this signal that's inside of the diamond. If the switch is not on, then A will be true. And the switch can't be both on and off at the same time, so this gives our desired behavior. Either C is true or A is true. Okay, and I think Davis is going to do this next example of
Yeah.
ASM.
Okay. So this is I guess a little crouched down, I guess. So this is basically like this is an example of some kind of state machine that you may see in real life. Well, I guess this isn't really perfect. He went in class of a washing machine ASM, and this is just like a simple drawing that you can like use these what's it called? Use these knowledge of ASMs to your technique. Okay, so create an ASM to count 1, 2, 3, 4 in LEDs. So I just said to use LEDs because it may get confusing with the count bits and whatever. So we're gonna have a box here. I'm just gonna block it out. So 4 LEDs. So we'll have 4 boxes.
Do you want a mouse, by the way?
No, I'll be fine.
Okay.
So I have 4 boxes that represent the count. Uh-oh. Undo, erase, erase. Okay. That will represent the counts. And inside of them, we'll just have LED 1, LED 1, LED 2, LED 3, and LED 4. So that's just going to represent our count going through the different states. And so now it says when the count is 3, check if S1 is true. So I'll have a little box, and I'll make it a diamond as a conditional S1. And so if it's true, immediately, so that means that there's going to be an oval because an oval is a mealy. Oh, I probably should make that bigger so I can write in it. Immediately activate LED 7. So we'll have LED 7. 7 go true and return to when the count is 1. So that means when LED 7 goes true, it's going to go back to LED 1. And the rest should be the same. So we'll go like this, and then we'll check S1. And if S1 is true, true, so that means we had a 1 here, it goes to LED 7. Otherwise, it'll go to LED 4. And then it'll go back to LED 1. So another thing, for this to be a proper ASM, we need state numbers. So this will be state 0, this will be state 1, this will be state 2. Remember, it's binary. This will be state 3. So I guess we should add a 0 in front of here, in front of here. And another thing is that give your states a name. You don't want to be just referenced. Should I call all of you by your UFID numbers? No. Have your states have a name. So I'll just name this like S1. Doesn't need to be something fancy. Just have a name so that it's easy. I think Schwartz uses the president names in his diagram, and that's kind of funny, but you can just name them whatever. So this is a proper ASM, and it should follow this pattern. Okay, what's next? I think it's your part, Daphne.
Okay, yeah. Okay. So let me change the thing for this one is,
Do you want to change to the double view?
yeah, that might be better.
Okay.
I'm going to try to write the next state truth table on the whiteboard.
Oh, it's sharing this one, this one. There we go. Okay.
Okay. So let me just write out like the columns. So, okay. First, I'm going to kind of run through like how would you interpret this truth table? So let's see. It's a little hard to read. This ASM represents a horse going through a race. So let's say you start here at 0, 0, 0. I didn't give these states names. You probably should, but just so you know, they all have unique state bits because you'll see that like a lot of these outputs are very similar. Like They have exactly the same thing in each of these boxes, but they are different states because they go to different, like, they go through different conditions or different states after um, you hit that state. So let's start at the beginning here. There is nothing inside this box, so we're not going to output anything. And then for we check based on inputs. So I guess if you wanted to start off by listing all of our inputs, you would look for everything that is in the conditional boxes. So two of our inputs are happy, is the horse happy? And wit, does the horse have enough wit to like to clear a certain quality in this race? So we have happy, wit, speed, stamina, and power. And so I'm gonna try to write these on a whiteboard here, if you can see them, so I can start writing out the state truth table. Um,
You see. Oh.
and as you can see in the corner of each state, we have three state bits. So we're going to need Q2, Q1, Q0. Actually, this might be. I'm gonna represent these with like the first letter abbreviation. So happy is gonna be H, wit is gonna be W, speed is gonna be SP, stamina is gonna be ST, and then power is gonna be P, and then we have Q2, Q1, Q0. Oh my gosh, I made this a little complicated. Can you guys see everything on the? Oh, where's?
I think it's okay. The marker kind of sucks a bit though.
Okay. I'll try to keep going with this. So this is our left-hand side. E2 plus E1 plus E0 plus. Then we want to look at what kinds of outputs we have. So the horse can have a late start, it could be rushed, and it can be sorry, we're looking at what is inside the circles or the rectangles too. So the things we have are late start, rush, half, and win. I'm gonna represent with the S. Is this entirely visible? Okay, it looks mostly fine. Okay,
What about end?
and oh. Okay. So we want to start at Q2, Q1, Q0 equals 0, 0, 0, right? And this is this is the very top state here. And so we can see that this conditional, like inside of this state, between this box and the boxes down here, the only inputs that we care about are happy and wit. So I'm gonna put don't cares for everything else. And then what you can see here is you can have a conditional that goes to more than two outputs, because if you have two variables going in, then you can represent the outputs as like here it says 0, 0. That means happy is 0, wit is 0. 0, 1 means happy is 0, wit is 1, and so on until 1, 1 means both of them are true. And so you'll have one row one row for each of these possibilities of outputs. So let's say it's 0, 0. This means that late start is going to be immediately true. So we're going to put a 1 over here. This is late start. None of the other outputs are going to be true except for that. So we're going to put 0 in literally everything else. And our next state is going to be 0, 0, 1 because it flows to this one. So this is a rectangular box with half of it, but it is different from all of these other rectangular boxes with half in them. So we'll put 0, 0, 1 as the next state bit. So let's go through the other few. So if happy is 0, is 1, none of these other sets matter, and I'm just going to fill out the other ones of these in counting order. This is also the same starting bits. Let's say if happy and wit is 0, 1, we go to rush. Rush is true, nothing else is true. So you can see only the rush bit is here that outputs. And then the next state we go to is 0, 1, 0. Let's say happy wit is 1, 0, then late start is also true. And what you can do is you can have multiple states going into, or multiple conditions going into the same state. So you can see there's an arrow that points from this state to the, I think that's 0, 0, 1 state here. You can do this if you have like two like logic flows that go to the exact same like state afterwards. Like, yeah, if you have multiple ways to get to the same like sequences of events, then it makes sense to just like have multiple things going into like one state bit, right? So, or one state. So we're gonna say that like if we flow through it like this, it still goes to 0, 0, 1. And finally, the last path that we can go through is if happy and wit is 1, 1, then we will have no outputs for this like entire state. So I'm gonna put 0, 0, 0, 0, 0. And our next state is going to be 0, 1, 1. So now let's go through each of these possible states. So we're gonna try to go through this vaguely in counting order. So the next states that we're gonna cover are 0, 0, 1. If you look over here, half or 0, 0, 1 goes directly to 1, 0, 0. And the only thing that's going to be true in this state is half. So this goes to 1, 0, 0. Only half is true, nothing else. And we have don't cares on all of these inputs because there are no conditionals. So next, we want to see what happens if we are at state 0, 1, 0, which is here. And it is exactly the same thing, except the next state we go to is 1, 0, 1. So let me write this down. Our next state bits are going to be 1, 0, 1. The only output that's true is halfway through the race. And we don't care about inputs. Finally, we'll go through for 0, 1, 1. It's the same thing, except we go to 1, 1. So 0, 1, 1. The next state bits are 1, 1, 0. Half is true, nothing else is true. And all of our don't cares. Okay. Now we have 3 more states to go through. The next state we can go through, 1, 0, 0, end is always true. Then we check, is speed true? So this represents, does a horse have enough speed to win? If it's true, then the horse will win, and it'll go back to this state bit up here, or this state up here. If it's not true, it'll still go back to the state, but the mealy output, win, will not be true. So the way we can represent that, let me write 1, 0, 0, let's see if it's here. We only care about speed. If we started off with a late start here, we only care about if the horse has enough speed to win here. So we're gonna put don't cares for everything except speed. And we'll do the case first where speed is 0. In both cases, it's going, like the speed of 0 and the speed is 1 is going to go to the state 1, 1, 1. But since speed is false here, first of all, end is true because that's inside of the rectangular box for the state here. It's the more output for the state. Because speed is not true, the horse is not going to win, so nothing is going to be true. And if we do the same thing, except we say that the speed is 1, has no speed, and the same state, it'll still go to the state 111, but the horse will in fact win. So I'm gonna try, it's kind of vaguely the same thing for all these other bits, so I'm gonna try and go through them quickly. So for state 101, we're at the end. We're going to go to 111 for all the remaining states. We're at the end. When will be false if speed is false? And when will be true if speed is true over here? And then our final statement to cover, sorry, this is kind of long, but we just have to do almost final actually. We still need to cover 111. But 110, we don't care about any of, oh, sorry, this was supposed to be 101 is different because the conditional, like, whether it goes to win or not depends on stamina. So I'm going to like shift this over a tiny bit, but still like the same idea. I'm also going to shift this one over because it depends on power. So if power is not true, horse will not win. If power is true, the horse will win. And finally, our very last statement, we have to go all the way up here to cover all the possibilities. There are no outputs that are going to be true. We don't care about any of the inputs. We know that the state bit is 111 and it goes to 111, it goes to 000. So let me represent this. We have 5 don't cares. The current state bit is 111, and we go to 000, and all of the outputs are false. Yeah, and I'll take a picture after this to send if looking at this entire table would help anybody. Yeah, enjoy. So the next question that's kind of relevant for this is what size ROM is required to store this next state truth table? So for that, we have three variables to consider, right? So we have the number of inputs, the number of state bits, and the number of outputs. So we have 1, 2, 3, 4, 5 inputs. I don't know if you can see that. I'll actually just write this on here. Okay. The number of inputs we have is 5. State bits, I'll write this SB equals 3. Outputs is we have 5 again. And let's see. When you say that a ROM stores an X-state truth table, that means that like a ROM, the way it works is you give it an address and it'll output the data at that address, right? So you have a certain input and you want to get a certain output. So the way that kind of works is this entire half of the truth table from the inputs to the initial state bits is going to be the address of, it's going to be represented by an address going into a ROM. And this entire half is going to be the output of that ROM. So the next state bits, as well as the outputs, are going to be the data stored in that ROM. And so we normally represent the size of a ROM by the number of addresses, like, actually, I'm not going to give a specific example. You might have 2 to the n addresses times m bits in that address. And so what this means is if you imagine ROM kind of like this. So you have a bunch of rows. There are 2 to the n rows, and each row has m columns. So this is saying we choose the row that we're looking at with like the inputs and the state bits. And each different combination of inputs and state bits is going to give a different output, and the output is going to be of size m here. So I guess ultimately the way to think about this is if you have, we've kind of already got, I hope I've kind of explained, like the address is going to have the bits in the input, the bits of the inputs and the state bits, right? So if we count here, that has 1, 2, 3, 4, 5, 6, 7, 8 things. It has 8 bits in the address. And so if there are 8 bits representing the address, that means that 2 to the 8 possible addresses can be represented by those 8 bits. So because like if there are 8 bits in a number and each of those bits can store like 2 pieces of information, that means there are like 2 to the 8 possible addresses, right? And so in this case, we would say that there are 2 to the 8 addresses. And then for the output, we're also going to look at it by bits. So we have, these are our output state bits, and our outputs to the system. So we have 1, 2, 3, 4, 5, 6, 7, 8 bits in like in the output of this hypothetical ROM. And so that means that directly we are going to have 8 data bits. And so if you were to expand this out, 2 to the 8 is 256, right?
I think.
So if we were to expand this out, you would need a ROM of size 256, which means 256 different addresses, times 8. And like this table does look a lot shorter because of all the don't cares we have, but you can imagine like you can't have, there's no such thing as don't cares inside of a ROM. Like you would need to expand this out to every single possibility of what these don't cares could be. And so that's why there would be so many like so many different addresses in this ROM. But I hope this makes sense as an explanation of like how you get the size of a ROM from the size of the NSTT. So if you want like a simple formula, the input is like the number of addresses is 2 to the power of inputs plus the state bits. And the data bits you need are just the outputs plus the state bits. Okay, I guess we're gonna move on to VHDL now after all that.
Do you all have questions about ASM next entry table or ROM? No?
Yes.
Yeah. Okay. All right, so we'll move on to VHDL. So VHDL is basically a way to skip using a BDF and skip using hardware. So it's really beneficial because you can save time overall with making your hardware. So like if I was to make for instance, a hex to 7 segment decoder, right? That probably took you a while in, I think it was lab 3, but if you can do it in VHDL really easily because it's just going to be a couple lines of code, and you'll actually do that in, I think it's homework 10, homework 11, something like that. But it saves time, and VHDL simplifies logic for you, so we can use that to our advantage to we can just chug in a giant unsimplified equation and it's going to be able to simplify it. And we're not going to need to do any K-maps on our own or make any mistakes. So with that comes this required text. So this is required in every single type of VHDL code, no matter what and how it works. So where's the mouse? Okay. So here we have these two. So this line, where is it? We have this line and this line, which are necessary. It's like if you learn Python, it's like an include or like for a library. Then this section here is basically how we'll identify our input signals. So that'll be everything that goes into our box. So you're basically making a black box, he likes to call it, is so anything in the entity is what goes into the black box, and anything in the architecture is what comes out of the black box. So that may not make much sense right now, but we'll go over that in a little bit. So easy VHDL. Easy VHDL, I would recommend you do this kind of VHDL for this lab, especially because if you try to get fancy, you may end up taking a longer amount of time. This VHDL is a lot easier to debug. So there's some stuff in the chat. Yeah, okay, perfect. So this VHDL is really easy to debug, and it's actually, I think it's the easiest way, which I call it easy. So, oh, I misspelled signal. That's funny. I'm gonna go ahead and stop sharing and share Quartus. Everybody loves Quartus.
Yay, Quartus.
And then, wait, we don't want that. Share this one. Quartus. Where's Quartus? Quartus. Share. Laptop HDMI. We want this side. No. Settings. Duplicate. Keep. Quartus. Okay. So, can I do a control plus? No. All right. So, can y'all see the VHDL easily, or should I zoom in? You can
That's
see.
good.
Okay. All right. So, like I said before, these lines are required. Oh, by the way, use a double dash as a comment. I'd recommend lots of comments because that's going to help you debug. So these are required. It's basically just explaining like Python import the logic and stuff. So then here, you're going to have your inputs, like I was saying earlier, and then here you're going to have your outputs. And so another important thing is this. So this name here, you can see it's used a couple times. It must be the name of this file. So when I go to save, I needed to name this VHDL file. Let's call it example. So when I save it as example in the Quartus project, all of these must become example with the same exact case, or else it will not work. Okay, so that's just the basics of it. So now we can go ahead and start our signals. So I low-key forgot it. So let me go back. So it says A in STD logic. Okay, so to define a signal, I just do a name and then STD underscore logic. And oh well, I forgot the keyword. So you need in. And that's just defining it as an input. And we can do this a couple times. So A, B, C, change these. B and C. And then we can do the same exact thing for outputs. So just change out into out, out, out. And then rather than A, B, C, we can do D, E, F. So that's just the basics for inputs and outputs. But now let's actually do some logic. So you can easily define logic. So in this section, the architecture, you want to define only the output. So I'll say the D signal, and then you use this funky looking equate for basically equals. And then I'm gonna draw. So an easy way to do this is SOP or POS. So I'm gonna do sum of products. So a way to do this is I'm gonna have basically something and oh well, yeah, something and well no, it's sum of products, so it'll be or something or something or something, right? And inside of these, we're gonna have a bunch of ands. So like and uh and and I can just copy this to here. Uh-oh. Let us see. This and like this. Okay. And now before all these ands, I can have a something like this. And then this. And then like this. Okay. So what we have, oh, I'm missing one. Like this. So in this bubble, now I can have a symbol. So let's say not A or not A, right? And then in here we'll have B, and then here we'll have not C, and then here we'll have, oh, there's only three, so I guess discard this. So what I was saying with how this makes it easy, you add a little comma, add an enter, and then a couple spaces. And then let's line these up here. So now if I copy and paste this here, and then add an enter, then get rid of these, I can just have a bunch of lines of this, or, and then let's do one more, or here. So when I'm making my table, let's add not, not, and not all. So like this. So this is the basic setup for a SOP, or yeah, for an SOP. And now what I'd recommend you do is when I'm gonna look at my truth table and I'm gonna say, okay, I see a one here at not, all three of these knotted, right? So okay, I'm keeping that in. Your expression here is when to output a one. So your output one is going to be true here. And then let's say there's another one at A, like A is true and then not B and not C. Rather than deleting this, I say keep the spacing so that you can automatically see, I'm going through this. I see, okay, this line is not. This line has a clear indicator of this truth value here with all the spaces you see. So this represents, okay, A and then not B and not C. And you can just go through and choose these. It doesn't really matter for the purpose of this example of like what outputs we actually have. But you'll get something like this, which is going to be your output, which is a MSOP. And so you can do the same for product of sums or yeah, POS. So I would just change this and instead of have these be ands and all of these be ors or But be very careful with your MSOP and MPOS because you may get confused. So I'd say just add like a comment, POS, and then SOP. So for the purpose of this lab, like I said before, VHDL will auto simplify for you. So all you have to do is look in your truth table and find the row and just plug it in. So you don't need to do any K-maps, anything like that. It'll be very simple. And so you just have your end behavior. Oh, another thing. Do you see this semicolon here at the end of our entity? So technically, this semicolon acts as the end And so we don't need a semicolon here. You'll get that error. It's kind of dumb, I feel like, but it's just something that you'll pick up is that you ignore the last semicolon for the entity. And they'll give you in your lab quiz or the exam or anything, they'll probably get, oh, maybe not in the exam.
I remember having to write small snippets of VHDL, but not necessarily like the entity setup.
Well, yeah, but they'll give you like, I don't know if it's universal for pies, but when I took this class, there was like a example like with all of the syntax, so like the library.ieee,
Oh,
all this stuff, so that like when I was writing it in the lab quiz, I could easily remember.
I see. Oh yeah, I never took that lab quiz, so.
That's crazy. But yeah, so this is easy VHDL because you're just going in, you're writing each one, what's true and what's false, and assigning it to an output. And then another thing is a little trick that is important to note is the use of a signal. So signal is STD logic. So if I have all of these inputs, right, they're going to be on the ends of our black box. If you think about when Quartus is going to make this, these are all going to be lines you can attach to from the external Quartus world. But if I wanted to make something internally, right, I'd make something like called a signal. Let's call it G. And then let's have it as a, what did I say? STD logic. STD logic. So this signal is internal and can actually be extremely useful when it comes to active low and active high. So let's change D to be active low. And I'll say, okay, let's rename this signal, I guess, to be D. And we'll say D is not D active low. So what this does is it makes it so that when we use D internally here, oh, I guess I should probably change this slightly. When we use D internally here, wait.
Is that gonna conflict with the like the output that is D having a
Oh,
signal
I
in
guess
D?
you're right. So D active low is not D. So this way we can have an output be active low and it'll just be the inverse of our previous output. So we don't have to mess around in our brains with, oh, does this name make sense? Does this name make sense? Kind of thing. Because I feel like doing something like this is going to give you a lot less confusion than changing all of the logic around. So that is, I guess, if we want to show the funny photo. Uh,
Yeah, I guess another thing is
do you want
there
Quartus?
no, it's okay. I guess like there's very good example code for VHDL, and you kind of have the choice in your practicals. You can use either Quartus to represent your logic with like actual parts, or you can try and use VHDL. What happened to me during the course, I kind of just wanted to say this, is like I relied very heavily on the example code and I didn't like totally understand, or it was more like I couldn't recall how to like write out all of the example code. If you do that, you probably won't be able to get the benefit of using VHDL in your practical or whatever, which is it might be simpler for you to like to implement the equations directly from like a truth table instead of having to do K-maps and the debugging and all that. So like I guess like you should kind of make a decision, which is do I want to use VHDL in the future, like later in this course? And if so, like probably try to learn the syntax, like the entity architecture is stuff. Like have it committed to memory, try writing it, like practice writing it from your head, like without looking at the example code or whatever. Or do you want to focus on just using Quartus like you've already done in this course, which like I can't say for sure because he may or may not test you on further parts of VHDL, but I believe like on exams and stuff, you're mainly going to have to write out like how like the equation we did was like D equals and then some logic equation. The extent of what you're going to have to use in VHDL is probably not much more than that. You're probably just going to have to represent logic with it. So I guess what I'm trying to say is decide now if you want to, well, decide at some point if you want to like learn the scaffolding and stuff. But yeah, with that out of the way, if anyone has any questions, feel free to ask them now.
Do you have anything VHDL?
Yeah.
You have ASMs for us to look at?
Yeah, we can look at any ASMs for that 5.
Yeah. Yeah. My phone.
What's just the evening goal to yeah. Once it is immediately the most of the so we see that
Will you guys be revising our ASM designs for lab 5? I think for the people online, it would be easier if they like DM'd it to one of us over Slack.
Yeah, well, I don't know, like, yeah, we can't look over it now, but if they send it to us or come to office hours, we can look at it.
Yeah, I guess like if you're on Zoom, then it's not really possible for us to look over them without like you showing it to everyone else, and that's like not very academically honest. But I think you can DM it to me, or are you okay with?
Yeah.
Yeah, you can just DM it on Slack to one of us, and we're gonna be here for a bit longer, so we can totally look over it. Yeah.
Okay. So with that out of the way, there's my favorite part now is advanced VHDL. So this is not taught in the course and no pi taught me this, but I got some digital design students to teach me I don't know how you learned it, but I got some DD kids to teach me advanced VHDL. So don't use this for this lab 5, but it may be useful to use with labs. Oh wait, no, I guess he does include vectors, but nothing with the bus signals. So this stuff I would say don't use for lab 5, but maybe use on homework 10 or on what's it's 6 for the GCP? No.
Lab 7 is using the GCPU. I think you can use this in lab 6 when you
Yeah,
like
when you make the instruction register,
yeah.
that's it. Okay. So now we go back to Quartus. We have the secret code at the end. So there's you can do instead of just having something like A is like input and then STD underscore logic, you can do bus. So I'll have bus is a input STD logic underscore vector. So this represents that we have a bus signal that's going to be multiple signals that is made up. And then we'll have, I guess I need to change this example. So it would actually work example. And then this would be we can have we'll just have, what did I do in the PowerPoint? Bus and enable. Okay, so enable is an input, and it's just a normal one. So now what you can do is you can do I guess this is a reserved word. So what should I call it? Output? Out. Okay. So then you can do I forget these, it's with but output and enable select, and then you can do your normal. Okay, so now we'll have an output uh uh H is our out std underscore logic. And we can do, so H is a 1 when, and then for instance, so in this example, we've created a bus. We're creating an imaginary bus with the uh output. Oh, well, I think we also need, yeah. So we'll need to specify the size of the bus, for the output bus. So I'll just say 2 down to 0. So what that means is that this bus will have three line bus, and then this is just a normal signal. So when you do this, it generates a 4-line bus where 3 through 1 are the output and 0 is enable. So you can then write it something like 0, 1, 1, 1, or 1, 1, 1, 1, uh, or 0, 0, 1, 0, or something like that. And then you can do 0 when, and then like I can I don't know, just come up with other ones, 1, 0, 1, 0, or 1, 1, 0, 0, or something like that. And then lastly, I'd recommend you do X when others. So what this basically does is you can have, and then you just copy and paste this for any of the other signals that you would want to do. So this makes it, I say, a lot, it saves you even more time, because rather than having to do the advanced, like, not A, not B, not C kind of thing, you can just write out when it's like 0, 1, 1. And I think that'll just save you a lot of time rather than have to type all this stuff out and copy and paste, which is why I preferred this method. And you'll use it later on if you continue down the embedded systems track or FPGA track when you do Verilog. So all this stuff is pretty useful down the road, and I think it's extremely interesting to learn.
Yeah, and I think it's just a lot easier to debug this kind of thing if you can like you're less prone to missing, like, oh, I forgot a knot there. You can actually see like if it corresponds to the truth table rows.
Jacob, I would not recommend you do this on a practical. Um, or like if the practical uses VHDL, like don't use the advanced method, because if you don't, like, he's not going to give you this definition in the, like, if he does give you any like example VHDL code, this kind of stuff is not going to be in there. So if you forget it, like, then you're kind of just cooked.
Yeah, like it would have to be something again you like actually commit to memory. So this is lab speedrunning material.
Lab speed running material, if you had a giant box or something to make, I guess, speed run that too.
Yeah.
And then this recording will probably be posted a couple days later, maybe like Friday, maybe at most Sunday.
Yeah. Hopefully by Friday or Saturday.
Yeah.
Hopefully we can expedite it this time.
Yeah, I mean, I'm probably just gonna upload it tonight and then have Shorts check it.
Okay.
So that's all I had. If y'all have any more questions, now's the time.
Yeah, and has anyone sent over their ASMs?
Not to me. Oh, well, Jacob did.
Okay.
If you want to look it over.
Oh yeah, I got someone's. Yeah. Okay. I'll try to respond to them just like if we for sure don't have any questions. But I saw someone did send me one, so. Yeah. Mm.
How's your labs going? Have you started?
No, this is my initiation.
Yes, something I want to say is like, in particular, the technique of having an empty box and then having a conditional that is connected to like mealy outputs. So like not actually giving the output until like you've checked something is extremely useful for this lab. Like I would say if you don't do that, you should like double check your work. Because if there are conditions, like if there's any sort of condition where like you need to immediately do something and that thing involves like only one thing being true, then that means you can't have like something that's true for the entire state, if that makes sense. Because then you'll have like another thing true and like that thing in the state is also true and it clashes and it's not good. So I think in particular, only one of green, yellow, or red should ever be true at the same time in your lab 5. So make sure that like trace through your state machine logically and make sure that you never have a condition where two lights on a traffic light are on the same time, because that would obviously be very confusing and bad. So yeah.
Mhm.